you, Chairman, and good morning, everyone. My name is Shu Kagami. I'm from Denso Corporation. I will give my presentation on the topic of fatigue behavior of high-strength steel in diesel oil. As shown on this slide, I will talk about the background of the study, method used in the experiment, and the result of fatigue test. Let me begin by explaining the background of our research. Recent developments in automotive technology have led to the growing use of automobiles all over the world. Specifically in Europe, the percentage of diesel cars is on the rise, as shown on this slide. A trend in diesel cars is the use of higher fuel pressures with an aim to reduce emissions and improve in thermal efficiency. It is a response to emission regulations becoming increasingly tight each year. Meanwhile, fuels used in diesel cars have diversified, including biofuel and synthetic fuel. Moreover, users in some regions have been seen to use inferior fuel containing soda and ash. There is evidence that the stress on fuel injection parts increases with increasing fuel pressures, and the strength of the parts decreases with increasing use of aforementioned various types of inferior fuel. Consequently, there are concerns about decline of the strength safety factor of parts resulting from these phenomena. Although it will be necessary to take these effects into consideration in a strength design of parts, there is no definite mechanism working in decreasing material strength under the effect of fuel. Thus, to ascertain accurate material strength in fuel, this study first established a fatigue strength evaluation method in fuel. Subsequently, this study aimed to examine the mechanism working in declining strength in diesel oil by clarifying fatigue characteristics in fuel. Next, I will explain our experimental method. We used chromium molybdenum steel. Its chemical composition is shown on this slide. Around about 45 mm in diameter was cut into specimens with these dimensions. Specimens were heat treated in a vacuum carburizing process. After the heat treatment, the surface viscous hardness and surface residual stress were shown on this slide. In the fatigue test, the stress was applied in 4.1. The test frequency was 20 Hz, and the stress was applied in a sine wave at the stress ratio of 0.05 and up to 10 million cycles. The maximum bending stress on specimen surface was calculated by the formula shown on this slide. We used a servo-hydraulic fatigue testing machine, which is shown on this slide. To avoid fuel leaks and evaporation, the testing chamber must be tightly closed. For this purpose, 4-point bending jig was enclosed in a grip pipe, and wrap was used to seal, enabling the fatigue test to be conducted in a closed space. For the test, we newly constructed a fuel circulation system. The schematic view of the system is shown on this slide. In this circulation system, fuel is pumped out from a tank via circulation pump and sent into testing chamber explained previously. The testing chamber is filled with fuel and fuel returns to tank through a discharge pipe. For the fuel, we use diesel oil, complying with Japanese industrial standard. The diesel oil was heated in a controlled manner to maintain the testing chamber temperature at 80 degrees Celsius. One point to note about the fatigue test in diesel oil is that an extended period of the same fuel causes excessive fuel degradation. And therefore, it is necessary to ensure stable fuel properties in the testing chamber during fatigue test. We estimated the most degraded diesel oil condition in the field to be a total ash number of 0.25. In this study, we changed the fuel to keep total acid number below 0.25. We analyzed fuel degradation against test time. The result of analysis is shown on this slide. Accordingly, we decided to change the fuel within 8 days. Next, I will explain the result of fatigue test. This slide shows the result of fatigue test conducted in diesel oil, plotted as an SN diagram. This slide also shows the result of fatigue test conducted in air for comparison purposes. The number of cycles is plotted on the x-axis and stress range is plotted on the y-axis, both on a logarithmic scale. The staircase method was used to determine the fatigue limit. Open marks indicate unfractured specimens, and solid marks indicate fractured specimens, both at 10 million cycles. The results revealed that fatigue limit in diesel oil was approximately 100 megapascal lower than that in air. After the fatigue test, we observed fracture surfaces with them to investigate the cause of the differences in strength. These photos present an example of fracture surface image. The photos on the left are from testing in air, and those on the right are from testing in diesel oil. Under all test conditions, there are two fracture origin patterns from inclusion at grain boundary and from surface grain boundary. Variation in test environments caused no difference. Meanwhile, no corrosion marks were observed on the fracture surfaces from testing in diesel oil. We rearranged the SN diagrams according to different fracture origin patterns revealed in the formation fracture surface observation results. The SN diagrams were grouped into two patterns. More specifically, in low cycle range, fracture initiating from surface grain boundaries indicated higher fatigue strength in diesel oil than in air. Meanwhile, in high cycle range, fracture initiating inclusion at grain boundary indicated lower fatigue strength in diesel oil than in air. We checked the specimens for cracks during fatigue test in order to investigate whether changes in the strength of the specimens in diesel oil were dependent on crack initiation or propagation. During this check procedure, we studied testing, stopped in midstream for observation, and restarted the test. Two stress levels were used in the test. White circles indicate specimens were free of cracks, and X marks denote fracture. Conducting the test this way, life before crack initiation was approximately 90% of fracture life. So changes in the fatigue strength is dependent on variation in crack initiation life. And to examine the effect of diesel oil on the specimen surfaces, we conducted an EPMA analysis of surfaces under tensile stress. Using these specimens, each fractured in high cycle range and exhibited strength differences. The results revealed that specimens tested in diesel oil had higher concentrations of elements O, Si, and C than those tested in air. From these results, although it is necessary to investigate further in the future, now I think the cause of the fatigue strength reduction in diesel oil is this slight corrosion and grain boundary enrichment due to hydrogen generated by corrosion. Meanwhile, in high cycle range, degradation of diesel oil is progressed with time during fatigue test. Therefore, it is highly probable that degradation of diesel oil has some effect on specimen surface. In contrast, specimens fractured in low cycle range were not subjected to degraded diesel oil because the test ended within 1 day. As a next step, we conducted a fatigue test in relatively high stress range so as to cause fatigue breakdown at the low side. Using diesel oil degraded through about 8 days. Green marks represent the result of fatigue test. In degraded diesel oil, specimen exhibited fatigue strength was shorter life in low cycle range. Therefore, these results suggest that the degradation of diesel oil is considered as one of the important contributing factors in reduced fatigue strength. Lastly, I will present the conclusion of this study. Firstly, there were no corrosion marks in the specimen in fuel, and fatigue limit in diesel oil was 100 megapascal lower than that in air. Secondly, regardless of the fatigue test environment, the fracture origin is low cycle range exhibited surface grain boundaries, and that in high cycle range showed inclusion at grain boundary. Thirdly, the concentrated parts of the O, Si, and C were observed on the specimen surface and tested in diesel oil. And finally, the degradation of diesel oil is considered as one of the important factors to explain the degrees of fatigue strength. Thank you for your kind attention.